In this video, we're going to complete the KutaSoftware Infinite Calculus free worksheet horizontal tangents. So our directions for numbers 1 through 4 are for each problem to find the points where the tangent line to the function is horizontal. But let's really think about what this is saying. So we're finding the points where the tangent line to the function is horizontal. So in order to have a horizontal line, what does the slope have to be? 0, right? The slope has to be 0 in order to have a horizontal line. So if we're trying to find horizontal tangents, remember, tangent line is formed by using the derivative at any given point. So the derivative of our function helps us get the slope at any given point. So we just need to figure out when the derivative, which is a way of finding the slope, is equal to 0, right? Because a horizontal line has a slope of 0, so we want to find when the derivative, which the derivative helps us find the slopes of our function, is equal to 0. So in a nutshell, what we're going to do is we're going to take the derivative and set it equal to 0 to get that horizontal tangent. So let's look at number 1. Not even needing to take the derivative, you can see that we have a horizontal tangent, so a tangent line with a slope of 0 at this point here. And remember, tangent lines only touch the function at one point in that general vicinity. So our slope is 0 right here at this point, -2, -2. So -2 in the x and -2 in the y. But if I was actually to calculate this out, I know that -2 is my answer. Let's look at, though, taking the derivative. So taking the derivative of y, we'll have, well, if we look, -x², the derivative of -x² is going to be -2x minus the derivative of 4x is 4, and the derivative of 6 is 0. So we want to see when the derivative, -2x minus 4, when does that equal 0? That's what we're trying to solve for. So we're going to solve for x. -2x, adding 4 to both sides, equals 4. Divide by -2, we get that x is equal to -2. And that is confirmed by what we found by looking at the picture. Now to find the y value, remember, we just need to plug it back into our original function. So we'll plug -2 back in. So y is going to equal -2² minus 4 times -2 minus 6. So y is going to equal -2² is a positive 4, but a negative of that is going to be -4 plus, because I have a negative times a negative, that's going to be +8 minus 6. -4 plus 8 is a positive 4, and 4 minus 6 is -2. So y is also -2, which is confirmed in our point, -2, -2. So let's move over to number 2. In number 2, we're going to be doing the same kind of concept. Let's first just look at the graph. So you can see that a horizontal tangent will occur at this point here, which is the point 2, 3, and it's going to occur at this point here, which is the point 0, -1. So I have two separate points where that tangent line is going to be horizontal. And quickly, just so you can see, let's think about this tangent line. If I drew a tangent line here, so it would be a positive slope. Up here, we'd have a positive slope, but it'd be a little bit smaller. Up here is where the turn occurs, and then we start going negative. So a change of a positive, and then all of a sudden the slope's negative, you know, going from positive numbers to negative numbers, you have to cross over 0 at some point because this is a continuous function. So again, looking at this leftmost horizontal tangent line point, I can see that my slope is negative, 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 and then all of a sudden the slope becomes positive. So where it switches over from negative to positive, I will have a horizontal tangent line, because going from the negative numbers to positive numbers, I have to cross over 0. So that's just another way to think about this. But let's confirm these 2 points by finding the derivative. So the derivative, y prime, or dy dx, is going to be equal to the derivative of negative x cubed plus 3x squared minus 1, which will be a negative 3x squared plus 6x. Now I can pull out a 3x from each of these terms. So I'll have 3x times negative x plus 2. Now remember, we're trying to find when we have a horizontal tangent line, which means that the slope is 0. So we're going to figure out when this derivative equals 0. So we have to ask ourselves, when does 3x equal 0? And when does negative x plus 2 equal 0? Because those are two different factors. So when either of those equals 0, our equation's 0. So 3x equals 0 when x equals 0, and negative x plus 2 equals 0 when x equals 2. And we can confirm that by looking at our picture. X equals 0 and x equals 2 gives us our two individual points where the tangent line is horizontal, but not the full point. We only have the x coordinate of that point. So let's plug 0 and 2 into the original function to solve for y. So in the case of plugging in 0, y is going to equal negative 0 cubed plus 3 times 0 squared minus 1, which 0 plus 0 minus 1 gives us a negative 1. So when x is 0, y equals negative 1. And plugging in x equals 2, we'll have y equals negative 2 cubed plus 3 times 2 squared minus 1. I'm sorry, I'm going off the page a little bit, so I'll move over some. So we have that y equals 2 cubed is 8, so we have a negative 8 plus 2 squared is 4, 4 times 3 is 12, and then minus 1. Negative 8 plus 12 is a positive 4 minus 1. That will give us a y value of 3. So again, our 2 points are 0, negative 1, and 2, 3. That's where our function has horizontal tangent lines. Let's move on to number 3. Now in number 3, we won't be able to see this visually like we did in numbers 1 and 2. However, we're going to still do that same concept. We're going to take the derivative, set it equal to 0 to find the x coordinate, and then find our y coordinates to get all the points where our function has a horizontal tangent line. So taking the derivative, negative x cubed will be negative 3x squared, plus x squared will be 2x, and 2 will go to 0 when we take that derivative. So I'm going to pull out an x from both of these. So we'll have x equals negative 3x plus 2. And this is our derivative, so we're going to set that equal to 0 to figure out when our slope, our derivative, is equal to 0. So I have two separate factors, so that's when x is equal to 0, and it occurs when negative 3x plus 2 equals 0. Which, solving for this, that's when negative 3x equals a negative 2, so that's going to be when x equals a positive 2/3. So I have two separate points, 0 and 2/3. So 0 and 2/3. Now I just need to find the y values for each of those. So if I plug in 0, I'll get 0 cubed plus 0 squared, which is 0 minus 2. So y is going to be negative 2 when I plug in 0. So that was the easy one to figure out. Let me cover up some of this so we can do the y value when x is equal to 2/3. That one's a little bit trickier and it's going to require us finding a common denominator. Y is going to equal negative 2/3 cubed plus 2/3 squared minus 2. So 2/3 cubed, 2 cubed is 8, 3 cubed is 27, and we have a negative 8/27 because that negative is on the outside. And then 2/3 squared is going to be 4/9, and then I'm going to subtract 2. I'm going to need to find a common denominator before I combine these. So I'll make that common denominator my 27. So I'll leave the first term as negative 8/27. My next number, I'll multiply both the numerator and denominator by 3. So that will be 12/27. And then for my whole number 2, I'll multiply that by 27/27. 2 times 27 is going to be 54, and that's all over 27. Now, -8 plus 12 is going to be a positive 4, and 4 minus 54 is going to be a -50. So my y value equals -50/27 when my x value is 2/3. So my 2 points are 0, -2, and 2/3 -50/27 for the points along my function where I have a horizontal tangent line. Let's go ahead and move on to number 4. And again, let's clear some of this out so we can go ahead and have room to work. So our horizontal tangent line occurs when the slope equals 0. So when the derivative equals 0. And for number 4, we can find the derivative one of 2 ways. We can do the quotient rule, or we can do the chain rule by rewriting it. I prefer doing the chain rule, so I'm going to rewrite this as x squared minus 1 to the negative first. So taking the derivative of that, dy dx is going to be equal to -1 times x squared minus 1 to the, we got to drop that exponent by 1, so -1 minus 1 is going to be -2, and then chain rule, so we took care of our outermost function, which was this raised to the -1, but now we have to take the derivative of our innermost function, which is x squared minus 1, and the derivative of that is going to be 2x. So I'm going to rewrite this derivative as a -2x all over, moving this negative exponent as a positive in my denominator, x squared minus 1 squared. And real quick, just to show you that that's what we would have gotten when we did the quotient rule, I'll go ahead and draw a little line here. Low d high, so x squared minus 1 times the derivative of 1, which is 0, minus high, which is 1, times the derivative of our low, which is 2x, all over low squared, x squared minus 1 squared. This is going to be equal to -2x all over x squared minus 1 squared. So you can see, it doesn't matter which way you take the derivative, you're going to get the same result. So continuing on, why did we take the derivative? Well, we care when the derivative is equal to 0, because that's when our slope is 0. So we care when this equals 0, which we care about as far as our fraction goes when the numerator equals 0, right? Because at any time that numerator equals 0, the overall fraction will be 0. We just got to double check to make sure it doesn't make the denominator equal to 0. Because if the denominator is equal to 0, then our slope is technically undefined, which, think about having an undefined slope, that's going to be a vertical tangent line. But we care about when this numerator is 0 because that's going to give us an overall number that's 0, which will be a horizontal tangent line. So when does -2x equal 0? Well, that's when x equals 0. And let's double check. If we plug 0 into our denominator, we'd get 0 squared minus 1 squared, which would be a -1 squared, which would be a positive 1. So that doesn't give us something undefined, so we're fine to continue on with this point. So we have a horizontal tangent line that occurs when x equals 0. So 0 is the x value for that point. So plugging 0 in for x to solve for y, we get 1 over 0 squared minus 1, which equals 1 over a -1, which is a -1. So 0, -1 is the point at which this function has a horizontal tangent line. And if we wanted to see where it had a vertical tangent line, we would just set the denominator equal to 0, which occurs when x equals 1, right? Because 1 squared is 1 minus 1 would be 0. So when x equals 1, we have a vertical tangent line. Horizontal, we have a slope that's 0. Vertical, we have an undefined slope, so an undefined derivative. But we're not worried about vertical tangents on this worksheet, so let's continue on just finding the horizontal tangents. Our next set of directions say for each problem, find the points where the tangent line to the function is horizontal. Indicate if no horizontal tangent lines exist. When would no horizontal tangent lines exist? Well, to have a horizontal tangent line, that's when the slope's 0, so when the derivative equals 0. So not having a horizontal tangent line means that the derivative will never equal 0. So let's see if we have any of those. Let's jump into number 5. In number 5, we have y equals x cubed minus 2x squared plus 2. So the derivative of y with respect to x is going to be 3x squared minus 4x plus 0. Simplifying this down, I'm going to get, pulling out an x from each term, 3x minus 4. So I'm going to see when this is equal to 0. So that occurs when x equals 0 and when 3x minus 4 equals 0. So I'm going to have two separate points, when x is 0 and when x is, let's solve real quick, when does 3x adding 4 to both sides equal 4? Dividing both sides by 3, that's when x equals 4/3. So my two separate x coordinates are going to be 0 and 4/3. So now I just got to solve those y values. So plugging 0 in to our function, and we're taking that and plugging it back into our original function. If you take 0 and plug it back into your derivative, you should get 0. Same with 4/3. If you take 4/3 and plug it back into our derivative, we should get 0, because that's how we got those points. So we're going to take those x coordinates and plug it back into the original function to get the coordinate, or the point at which we have a horizontal tangent line. So y equals, plugging 0 in for x, 0 cubed minus 2 times 0 squared plus 2. So y is just going to be 2 when x equals 0. Now, solving for when we're plugging in 4/3, we have 4/3 cubed minus 2 times 4/3 squared plus 2. So 4 cubed, 4 times 4 is 16. 16 times 4 is going to be 64. So we have 64 over 3 cubed, which 3 times 3 is 9, times 3 is 27. So 64 over 27 minus 2 times 4 squared, which 4 squared is 16, so 2 times 16 is going to give me a 32, all over 3 squared, which is 9, and then I'm going to be adding that to 2. So for this, I'm going to need common denominators in order to solve. And that common denominator, like with problem number 3, is going to be 27. So I have 64 over 27 minus, multiplying both the numerator and denominator of my second term by 3. That's going to be 96 over 27 plus, this is going to be 54 over 27. So I have 64 minus 96 plus 54. That's going to leave me with a positive 22. So 22 over 27 will be the y value for when x is 4/3. So 22 over 27 is my y coordinate. So my 2 points where I have a horizontal tangent line are 0, 2, and 4/3, 22, 27. Let's move on to number 6. In number 6, let's start by taking the derivative, because those horizontal tangent lines are when the slope is 0, so when our derivative is 0. So dy dx, the derivative is going to be, well, negative x cubed goes to negative 3x squared, plus I'll leave my 9/2 out in front, and then I take the derivative of x squared, which is times 2x, and then minus 12, because the derivative of 12x is 12, and then the derivative of 3 is 0. So everything should have been straightforward. Maybe you're a little confused on this one. I just broke this up and pulled the 9/2 out in front, and then took the derivative of x squared, because 9/2 is just some constant times x squared, or the coefficient of x squared. And you'll see that my 2 will cancel out with the 2 in my denominator. So I'll have negative 3x squared plus 9x minus 12. So what we're going to do is see when this equals 0. So what I can do right away is I can pull out a 3 from each of these terms to make it easier. And I'm going to pull out a negative 3. So pulling out a negative 3, I'll have x squared and then minus 3x plus 4. And that's going to equal 0. So I know that negative 3 will never equal 0. So the only time that my derivative will equal 0 is when x squared minus 3x plus 4 equals 0. So when does x squared minus 3x plus 4 equals 0? Let's see if I can factor it. What multiplies to give me 4 but adds to give me a negative 3? There's no two numbers that do that. Let's go ahead and do the quadratic formula with this one just to see. So if I had the opposite of b, which is 3, plus or minus the square root of b squared, which negative 3 is b, so that's negative 3 squared, which is 9, minus 4 times a, which is 1, times c, which is 4, all over 2 times a, which is 1. Aha! This is why we couldn't factor it. Look, we have 3 plus or minus the square root of 9 minus 16. Because 4 times 4 is 16. 9 minus 16 is going to give us a negative 7 underneath of that radical. Taking the square root of a negative number will give us imaginary numbers. So in the case of this one, in number 6, we have no horizontal tangent lines, or the horizontal tangent line doesn't exist. So no horizontal tangent line exists. So that's going to be our solution in number 6. And this is true because we couldn't factor it, and when we confirmed, we got a negative underneath of our radical when doing the quadratic formula. So there's no point in time where that derivative will ever equal 0 because the roots aren't real. So let's move on to number 7. In number 7, let's start by taking the derivative. So dy dx, and I'll go ahead and use the quotient rule for this one. So we have low, which is x minus 3, d high, so the derivative of, I'll leave this negative up there, so the derivative of negative 2 is 0, minus high, which is negative 2, times the derivative of low, which is 1, all over low squared, which is x minus 3 squared. So that's going to be, this goes away, negative of negative 2 times 1, or subtracting a negative 2 times 1 is going to be a positive 2 all over x minus 3 squared. So my question is, when does this equal 0? Well, it doesn't ever equal 0, because remember when we have a fraction, we only care about when the numerator equals 0, and 2 can never equal 0. So there's not going to be any horizontal tangent lines. So again, no horizontal tangent line exists. And that's because the slope, or the derivative, will never equal 0. Let's move on to number 8. In number 8, in this case, I'm going to go ahead and write this as a negative x squared plus 1 to the negative 1. And I'll do chain rule with this one. So bring down that negative 1, I'll have negative 1, so that's going to be a positive 1. And this is what dy dx is going to be, because now I'm taking the derivative after I rewrote it, times x squared plus 1 to the, well, negative 1 minus 1 is going to be negative 2. And that was just the derivative of my outer function, which was this raised to the negative 1. So now I need to take the derivative of the inside stuff, which is 2x. So in this case, I have 2x all over, rewriting this in my denominator as a positive exponent, x squared plus 1 squared. So we just need to see, when does 2x over x squared plus 1 squared, when does that equal 0? Well, that's going to happen when 2x equals 0. When that numerator equals 0, this overall fraction will equal 0. And that occurs when x equals 0. So we have one point, x equals 0. We just need to find that y coordinate now. So plugging in 0 for x, I'll get that y is equal to, and remember we're plugging it back into our original, negative 1 over 0 squared plus 1. Negative 1 over 0 squared plus 1 is going to be negative 1 over 1, which equals negative 1. So 0, negative 1 is the point of our function where we have a horizontal tangent line. So a tangent line with a slope of 0. Let's move on to number 9. So in number 9, let's take the derivative. And we're going to take that derivative using the chain rule. So the derivative of y with respect to x, I'm going to bring that 1/2 down in front, and then we're going to have negative 2x plus 4 still on the inside, and subtracting 1 from 1/2 will leave us with a negative 1/2. Now, because I did the derivative of my outermost function, which was my function raised to the 1/2, now I'm going to take the derivative of that innermost function, which is negative 2x plus 4. And the derivative of negative 2x plus 4 is going to be a negative 2. So simplifying my derivative down, negative 2 times 1/2 is going to be negative 1. So my derivative is actually going to be negative 1 over, I'll do the square root, of negative 2x plus 4. Because to the negative 1/2, I can write as to the positive 1/2 in the denominator, which is the same as writing the square root in the denominator. So we need to see, when does this equal 0? And, well, it's never going to equal 0, because negative 1, our numerator, is never going to equal 0, or 1 will never equal 0. Therefore, again in number 9, no horizontal tangent line exists. There's nowhere on that function where we have a slope or a derivative equal to 0. Now lastly, in number 10, we're going to bring in some trig. So, if our function is y equals negative cosecant of x, we need to take the derivative of that and see when that equals 0, because the derivative equaling 0 indicates that we have a horizontal tangent line at the point where that derivative is 0. So, dy dx is going to be equal to, well, what's the derivative of cosecant? The derivative of cosecant is negative cosecant of x cotangent of x. But because this is negative, and then I take the derivative and it's negative, I'm going to actually have a positive cosecant of x cotangent of x as my derivative. Now, they give me an interval from negative pi to pi because these are cyclical functions that continue on. But I don't really know what this looks like offhand, so let's simplify it down. Cosecant of x is really 1 over the sine of x. And cotangent of x is going to be the cosine of x all over sine of x. So you can see that when I simplify this down, I'll get that my derivative is equal to cosine of x all over the sine of x, that entire quantity squared. But remember, we're trying to figure out when the slope is 0, which is when our derivative is 0. So if our derivative is the cosine of x over the sine squared of x, we care about when that equals 0. So when does our numerator equal 0? So when does the cosine of x equal 0? Well, on the interval from negative pi to pi, if I was to draw my unit circle, if you like to look at a unit circle, negative pi is over here, negative pi is over here, here would be 0, and then continuing around would also be pi. So if we're looking at this interval, when does the cosine equal 0? And that occurs at these 2 points here and here, because that's when the cosine of x is 0. Pi over 2, and if we're swinging back the negative direction, or clockwise, negative pi over 2. So negative pi over 2 and pi over 2 are when the cosine of x is equal to 0. So we have two separate points. We have negative pi over 2 and we have a positive pi over 2 for our x values. So when x is equal to either of those, our derivative is 0. But remember, we need to see those y values as well. Y equals negative cosecant of x, and remember, a different way we could write that is negative 1 over sine of x. So I'm going to plug in pi over 2 and negative pi over 2 in for sine. Plugging in pi over 2, I'll get negative 1 over the sine of pi over 2, which the sine of pi over 2, right here, is going to be a positive 1. So negative 1 over 1 is going to give me a negative 1. So when I plug in a positive pi over 2, I get negative 1 as my y value. Now if I switch this up and plugged in a negative pi over 2, so now I'm looking at this angle down here, then that gives me a negative 1 for sine, and a negative over a negative will be a positive 1. So I have two different points in number 10 where I have a horizontal tangent line. That's negative pi over 2, 1, and pi over 2, negative 1. Those are my 2 points, or my 2 separate coordinates, where my derivative equals 0, which in turn means that my tangent line of my original function has a slope of 0. And with that, we wrap up this worksheet. If you have any questions, leave it in the comments below. And remember, the general idea of this worksheet is that a horizontal tangent line occurs when our derivative equals 0. So if you really understand that concept, these later concepts will make sense and be easier to visualize. And before continuing on, don't forget to like, subscribe, and share.